Again, the option now is that we want to solve equations, but before we can start talking about equations, we need to pause a little bit and talk about some properties. So like I said, let's look at this from a more algebraic perspective. Okay? So logarithms, they are inverse of exponentials. And as you know, there are some basic properties of exponentials, right? Like when you multiply two exponentials with the same base, what do? For example, you do x squared times x to the 3. What is that? X squared times x cubed. What is that equal to? X to the 5th. So what does that mean? When you multiply two exponentials with the same base, what do? You add the exponents, right? When you divide, you subtract the exponents. All of these little properties, they have a counterpart on the logarithmic side, okay? So that's what I'm about to write down now. So let me remind you the basic exponential properties, the rule of exponents that we're going to be referring to directly. So recall. So properties, let's see, the audio is on. So properties of exponents. I'm just gonna write down the relevant ones, okay? So let's see, this one, so assume that x is different than 1, and I should say b. So assume that b is different than 1 and different than 1 and 0. Okay, so what's b to the 0? This is 1. Then, so it has a logarithmic counterpart, okay? Then I guess, okay, this one is super silly, but it also has a logarithmic counterpart, so let me just write it. What's b to the 1? B, okay. So now if you have b to the x times b to the y, what is this equal to? B to the x plus y, right? And then if you have b to the x over b to the y, what is this? B to the x minus y. And then finally, if you have b to the x to the y, what is this? B to the x times y. So, in other words, 1 and 2, they are, hopefully everybody agrees with that. So number 3 says that when you multiply exponential with the same base, you add the exponents. When you do the quotient of exponential with the same base, you subtract the exponents. And here, when you do the exponential of an exponential, you multiply the exponents. Okay? Now, each of these, they're going to have a logarithmic counterpart. Okay? So, same way that, that these properties come along when you're doing some computations, then there are similar ones when you're dealing with logarithms that they will naturally arise. So, what I'm going to do is, I'm going to write down the properties and then we're going to justify them. Okay? We have the knowledge now to justify these properties, so let's do it. So, each of these properties okay, here should I say have or has? Because I'm saying each of these has, right? I'm saying each. So when I say each, I'm talking about a singular thing. Each of these, so at a time, right? Yes. Okay. So each of these has, I mean, it sounds strange because I'm using these, but okay, each of these has a logarithmic. Each of these properties has a logarithmic counterpart. All right. The thing is that since English is not my first language, I learn it by learning the rules. And then every time that I get these things,
yeah, you could also write that sentence as each of these properties have logarithmic counterparts. Which is
have logarithmic counterparts.
Yes, so you use has when it's singular.
Yeah, I think you're supposed to do that because it's supposed to be like the same instead of like choosing from here.
No, that sentence is grammatically correct.
Yeah, but I think it's supposed to be more
If you go with English, it's funny. It can go either way. That's right.
Okay, so okay, let's go. So each of these properties has a logarithmic counterpart. So write them down. So we call them, of course, properties of logarithms. And then, of course, I'm going to put others that do not follow strictly from here. There will be a total of 7, I'll say 8 properties. So there are 3 more that are not from here, but we're going to see why they are there. Okay, anyways, so you are responsible the same way that you were responsible to know these exponential properties, you are now responsible to know the logarithmic properties, okay? Because you will need them. Okay, so the first one. So log, again, in all of this discussion, b is a number that's different than 0 and 1. And then whenever I write x, that is a positive number. And then I will use an r as well. R can be any real number whenever it shows up. Okay, so the first one, log base b of 1. So let me put that here. X and y will be positive numbers. Log base b of 1, then log base b of b. Then I guess let's do log base b of b to the x, and then b to the power of log base b of x. Now 5 log base b of x times y log base b of x over y, and then number 7 log base b of x to the r. Okay, so let's go ahead and let's say what each of these things are equal to. Let's see, the first one, what is this equal to? 0. So it's equal to 0. And it's pretty straightforward to see why, right? It is because it follows straight from this property, because b to the 0 is 1. Yes? So this one right here is the logarithmic counterpart of 2. Okay, how about number 2? What is this? So when the argument and the base coincide, this is always 1, right? Why? Well, because b to the 1 is b, right? It comes from that property. Okay, now 3 and 4, this is basically what we discussed earlier, the definition, right? So what's 3 equal to? X. And what's 4 equal to? X as well. In other words, this is just saying that the exponential and the log, they cancel each other, right? These two, they follow by definition, since log and exponential and inverse function are inverse. Okay, so we have justified 1 through 4 pretty easily. There is really nothing to do. So the interesting ones, of course, are 5, 6, and 7. Okay, and then there will be a number 8 that we'll do at the end. Okay, so number 5. Basically, number 5, remember, this is talking about an exponent. Okay, and this is an exponent, and then an exponent of what? Of doing the product of something. Okay, so this is b to some power equals to the product of something, and this corresponds to a property that when you multiply exponential with the same base, what do you do with the exponents? You add them. So that means that if you do log of a product, this turns into a sum because you add the exponents. Again, we're going to justify this more formally, but I guess that would be an easy way to remember. The reason why you add is because when you multiply exponents with exponential, you add the exponents, and the logarithm is the exponents. Okay? That's essentially what happens. So basically, this is saying that logarithms send products to sum. Okay? They send products to sum. All right. On a similar note, this one corresponds then to the property that when you divide exponential with the same base, what do you do with the exponents? You subtract it. So logarithms, they send quotients to difference. This is log base b of x minus log base b of y. Okay? So they send products to sum, they send quotients to difference. And then for number 7, this one has to do with the one that you multiply the exponents. When you do exponential of an exponential, you multiply the exponents. Well, there are two exponents here. What are the two exponents that we have in here? R is an exponent, and the log itself is also an exponent, right? So this would be equal to the product of those exponents. So this is R times log base B of x. So we're going to take advantage of number 7, a log, to solve exponential equations, because basically this is telling you that if you are interested in the exponent of something, you can bring the exponent down by applying the logarithm. Okay? So for example, if you have 2 to the x plus 1 equals 5, and I want to solve for x, what do? The first thing that you need to do is you need to get rid of the 2, right? So we need to bring the x down from the exponent. Well, typically what we're going to do is we're going to hit ln in here. We're going to apply ln, for example. Why ln and not base 2? Well, because calculators typically don't have log base 2, but they have ln. Okay? We'll get to that pretty soon. And by doing that, when you use this property, then we can bring the exponent down. And now understand that ln of 2 and ln of 5, these are just numbers. Okay? So you can easily solve for x. This would be ln of 5 divided by ln of 2 minus calculator that allows you to compute this. Then, we don't really know. But however, every calculator, the same way that you have square root function, then every calculator you will be able to do ln, for example. That's why we typically want the answer to be in terms of either ln or log base 10, because those are the keys that you have in your calculator. Okay, but we're gonna do this later. This is what we're doing next. Okay, just wanted to show you how this property plays an important role in solving equations. Okay, any questions on the properties that we have here? For example, I'm going to just define number 5. Number 6 is going to be very similar to number 5, so I'm going to leave it to you as a homework. Okay, and then we're going to justify number 7. We already justified 1 to 4. Okay, so there's no reason to argue those. Okay, so let's prove this. So prove, so 1 through 4, they're already done. So 1 through 4 done. Then now let us prove number 5. So number 5 says that log base b of x times y is equal to log base b of x plus log base b of y. Okay? So let's try to see how, let's try to justify this. And the way you do this typically is you start with one side and then you do something, of course, and somehow you show that that will be equal to the other side. Okay? So let's begin from here. Now, remember that in all of these conditions, we have the fact that x is positive and y is positive, right? Remember that the assumptions that both x and y were positive numbers. So what does that mean? It means that x and y, you can think of them as being in the range of an exponential function. Remember, the range of an exponential function is from 0 to infinity. So any positive number, you can always write it as b to some power. Give me whatever number you want, I can always write it as 2 to some power. Do you understand this? Because the range is from 0 to infinity. That means every positive y has an x, so a 2 to the x is going to be equal to the y, as long as y is positive. Do you understand this? That's what the range is, the output of the function. So in other words, this x and this y, we can write it as b to some power. We don't know what that is, but we can write it as b to some power. So since x is positive, that means that I can write x as b to the m for some m. For some real number m, okay? And similarly, I can write y as b to the n for some n. Do you understand this? Yes or no? Yes? Okay, good. So now let's compute this. So with this understanding, if you want to do log base b of x times y, then this is equal to log base b of x to the n times b to the m times b to the n, right? Because remember, x is b to the n and y is b to the n. For some m and n, I don't know what these guys are. We're going to know what these guys are pretty soon. And then now here, why did I do this? Because I wanted to rewrite this as exponents, because now I want to use the properties that we know. So what do we know about exponents? What happens when you multiply these two guys? So this is log base b of b to the n plus n. right? Now, using one of the previous properties, remember, we already know 1 through 4. So what is this equal to? Log base b of b to the n plus n. What is that? This is just n plus n, right? They cancel each other, remember. Log base b cancels b to the x. Yes? All right. But now, what is m? Let's go here. What is m? Here is an exponential form. Rewrite this in logarithmic form. What's m equal to?
Log base b of x.
This is log base b of x. Yes? That's the exponent that you need to raise b to get x. Do you understand this? And what is n?
Log base b of y.
The log base b of y. That's the exponent that you need to raise b to get y. Does that make sense? Okay, so then we just prove that this is log base b of x because that's m, and this is log base b of y because that's n. So now if you ignore all the in-between steps and just look at the first and the last line, it follows that log of the product is the sum of the logs. Okay? Questions? So now you play a similar game with number 6. If you want to prove the quotient property, it's exactly the same thing. You do exactly the same. The only thing is that here you will have b to the m over b to the n, right? Using property of exponents, what would you have here? This will be a minus, right? And therefore, it will be a minus, and so you have a minus. Okay? So it's not really nothing mysterious going on. So that's number 5. Then number 6 is similar to number 5. So just try on your own. It's exactly the same thing. Are we okay? All right. Now let's do actually. And number 7 is again the same idea. Okay. So let's do number 7. We're gonna prove it also because it's gonna be used a lot to solve equations. So for number 7, so what do we want to show? We want to show that, typically when you want to argue something, it's good to write it down. What is it that you want? Well, I want to show this. Okay? So then, now I'm going to start with one side and show that it must be equal to the other. But now, hopefully, probably you already understand what to do. So, since x is positive, then that means that we can write x as b to the n, right? For some m. Which we know what it is. What is m equal to? This is log base b of x, okay? So since for any positive number, I can always do log of that, and that's the m guarantee, okay? If you want to think about it that way. Before I told you the range, exponential, and so on, another way to think about it is if you have a positive number, you can do log of that. That's the m guarantee, okay? That's that special power that you need to raise b to get the number m. So let x be equal to this. So then the left-hand side becomes log base b of b to the m to the r. Now, we use the corresponding property of exponentials. What do we know about exponentials here? What do we do with the exponents? We multiply them. So to the b, and then this is r times m. And what is this equal to? This is just r times m, but m is log base b of x. So that's r times log base b of x. So again, if you ignore the in-between lines, you just read the first and the last, it follows that if you do log base b of x to some power, basically what's going on is that the power comes down. Okay? That's the effect of doing log of some exponential expression. You're bringing the power down, multiplying. Okay? So that's that. Questions? Are you okay with this? So let's review the properties again, because now we're going to play a little game. The game that we like to play is the following. I give you a very condensed but could look complicated logarithmic expression, and then you need to expand it using the properties as much as you can. and also the other way around. I give you a very expanded, long expression, and then you need to write as a single logarithm. It's one little thing, okay? This one, writing as a single logarithm, is going to be beneficial for us right now when we solve equations. The one about expanding is beneficial if, for example, when you take calculus. There will be an operation that you're going to do, which is called derivative. To find the derivative of a logarithmic expression is easier if you have it expanded completely, okay? There is even a technique called logarithmic differentiation, that even if there is no log, you apply the log to make the derivative easy, okay? But you need to know these properties so that you can do that successfully. So we're going to practice that. So let's review this. Let's see, 1 through 4, they're just by definition, so those hopefully are easy to remember, right? There's really nothing to think about too much there. Now you really just need to memorize 5, 6, and 7. That says the log of a product is a sum of the logs, the log of a quotient is a difference of the logs, and the log of an exponential, it brings the exponent down, multiply, okay? We're going to play with these properties now. So, examples. So, write as a single log. So, write as a sum or difference of logarithms, and whenever possible, express any power as products, if possible. By the way, this is a mistake that sometimes students make. Keep in mind that there is no rule here. I'm not telling you what to do if you do the log of a sum. If you have log of x plus y, I'm not telling you what this is, because there is no property about that. It's not the sum of the logs, or it's not the product of the logs, nothing like that, okay? So these are the properties, so do not make up anything unless you justify and prove it, of course, okay? But if you have log of x plus y, well, that's x plus y. That's log of x plus y. There's nothing we can do about it, okay? So it says products to sum, and if you have a sum inside the parentheses, you cannot do anything about that. Okay, so let's see. Let's start with something straightforward. So warm up. Okay, let's do this trick just to start warming up. So for example, our job here is we're given a single expression, and then we need to write as a sum or difference. And if there are any powers showing up, then we need to write as products, okay? In this case, there are no powers, so we don't have to worry about it. So let's see. And of course, the idea is using the properties that we have above. So what do we see here? This is the log of what? What operation is happening here? This is a product, it's a multiplication. So what do we know about products? What do they turn into? They turn into sum. So this is equal to log of 3 plus log of x. Do you understand this? All right. Now for the next one, the property talks about the product of two things. But of course, if you have a product of three things, this extends to then the sum of the three things. If you have 20 things here as a product, then you have a sum of 20 things, right? So if you want, you can think of it as a two-step process. You can do log of 5 plus log of xy, but then log of xy is log of x plus log of y. So might as well just do it in one shot, okay? Questions? All right, so now in part C, by the way, notice how you always have to keep the same base. It's very important, okay? If you change the base, then these properties do not hold anymore. Now here we have a combination. So what operations are happening here? How many operations do you see in the argument of the log? 3. What are they?
Log base 2 of 5 plus log base 2 of x.
No, I mean, how many operations do you see here in the argument?
3.
What are they?
Log.
In the argument.
Oh, and 2.
2. What are they?
Product and
There is a multiplication and there is a division, right? There are only 2 operations, yes? Now, which one is more important? So which one do you think is the dominant operation here? Okay, for example, here there are 2 rules of logs that needs to be used. The question is which one needs to be used first?
the product. So it's part of the numerator. So you do that first.
So do you think that's the dominant operation? It's not a dominant operation. The dominant operation is a quotient. You have something over something. Right? That's the main operation that we're doing. Now it turns out that the stuff on top happens to be a little product. Do you understand what I'm saying? In this operation, the one that takes precedence, the one that dominates here is the fraction. In other words, if you're going to use the properties of log, you first need to split this as a quotient. And then you worry about the top. Because you see, this is something over something. Do you understand what I'm trying to say? Okay. So, this, we see it's a quotient, so you can write it as log base 2 of 5x minus log base 2 of y. You break the quotient. Now, when you break the quotient, you say, well, okay, this is already as simple as it gets, but now this one is a product. I can break it a little bit more. Yes? So, this would be log base 2 of 5 plus log base 2 of x minus log base 2 of y. Questions? Now, in this particular case, it turns out that because 5x over y can be written as 5 times x over y. If I were to write it like this, now the dominating operation is the times. Because it's something times something else. Right? Now, that something else happens to be a quotient. Now, because of this fact that these two things are equal, right? In that particular case, they are equal, then that means that then you could have, written log of 5, so do the plus first. Log of 5 plus this, and then this becomes log of x minus log of y, and you get the same thing at the end. You have to be careful because when the expression is more complicated, then we don't have this nice behavior anymore. So the order in which you apply the properties matters. Otherwise, you could get something completely different. So let me give you some examples. For example, practice a little bit more. So now I want you to try these things. Practice a little bit more. And then let's start throwing in some exponents into the mix. Okay. So remember, our job is to expand this as much as we can. So what can we do in D? What can we do here? Yes?
Do you want me to just give an answer?
And what?
Or do you want me to go like step by step?
Tell me step by step.
First you can split the numerator and denominator into log base 3 of 9x minus log base 3 of z.
Good.
And then you can split the first log into log base 3 of 9 plus log base 3 of x.
Good. Everybody okay so far? Are you guys okay with this? Okay, is there anything else that we can simplify here? What else can we do?
Yes, we can. The log base 3 of 9 is equal to, yeah, I had an error, so it's equal to 2.
Equals to 2. So this will be 2 plus, I mean, if something like this that you can simplify easily, then do it, okay? Don't leave it as log. It's like telling me, oh, the answer is 2 squared. Come on, the answer is 4, right? So it's 2 plus log base 3 of y minus log base 3 of z. Questions? Yes?
I thought that was an X.
Say that again?
I thought that was an X.
It's not like y, it's log x.
Oh, x. All right. Questions? Okay. How about the next one? What can we do? Anybody?
You can make it ln 2x squared minus ln y squared.
Okay.
And then ln 2 plus ln x squared minus ln cube, y cube.
Okay.
And then finally ln 2 plus 2 ln x minus 3 ln y.
Very good. So now at this point, we see these exponents. Remember the property that this allows you to bring exponents down. So whenever this happens, you can bring the exponents down. That's property number 7. So we'll get ln of 2 plus 2 ln of x minus 3 ln of y. Good. By the way, there is a little technicality here, and it's that this equality is valid as long as x is positive. Now, all of a sudden, we are saying that x cannot be negative anymore. It has to be positive. Okay? So, to be technical, the line on top is not exactly equal to this one because their domains are different. Okay? But typically, in this problem, we assume that all the variables are positive and so on, so we don't have to worry about these things. Okay? But because I didn't say it, then I should specify it here. Again, I'm not gonna be that picky in the sense that if you don't specify, it's fine, but you have to. I want you to understand that some things that needs to be said because we are claiming that those two things are equal, and as long as the variables are positive, yes, they are. Otherwise, they will not be equal. Okay, do you understand it? Was that clear? Okay, good. And then for the last one, we use the same idea. So I guess the point here is because we have a radical. What do we do when you see a radical? What's a radical? It's just a power. What power it is in this case? A 1/2. If you have a cube root, what will be the power? A 1/3, and so on. So remember, radicals are just powers. So we can write as a power, and then we do the same thing that we did, for example, in part E. Okay? So let's do that. So we can rewrite this as ln of x to the 1/2 over 2 times x minus 3 cubed. Now we activate the process. So break it into a quotient minus ln of 2 times x minus 3 cubed. So now the first one, we can bring the 1/2 down. Okay. Now here is a product that we can break as a sum, but be careful. There's a minus here. This minus is affecting the entire expression. Yes. So it will affect the entire sum. It will affect the entire sum. So I advise you to write parentheses so that you don't miss that, because this minus have to be distributed. Okay. Otherwise, you could write minus ln of 2 plus ln of x minus 3 cubed, and then that's wrong, because that plus that comes up here will turn out to be a negative really. Do you understand this? So you have to be careful. So, if you use the property, just put it inside a parenthesis so that it's clear what's going to happen. So now I'm going to do 2 steps in one. I'm going to distribute the negative, and then I'm going to bring the 3 down. Okay? So we distribute the negative, and then this 3 comes down. Are you okay with this? Again, there's nothing we can do about ln of x minus 3. It stays like that. Don't attempt to break it up. It stays like that. And also, if you have something like this, for example, even though you see a power, you cannot take it down. You can only take it down when you have the entire argument raised to a power. Here, it's only the x squared. But there is a plus 1. So that means the argument itself is the whole thing, and it's not raised to anybody. Okay? So there's nothing to take down. If you had a 5 here, for example, then yes, okay, that 5 can come down. But not the square. The ln doesn't have access to that x squared. Okay? Because there is a plus 1, so be careful. All right. Questions? Okay, now let's play the game backwards. I give you something like this, and your job is to write as a single log. But the same idea, you're just using the properties backwards. Okay? So this is, again, this technique is helpful. It will be helpful for you later. For example, in calculus, you're gonna need to do this kind of stuff. But now what we're gonna be relying on is actually the example number 2. Right, as a single logarithm. 2 log x plus 1/3 log of 1 minus 3 minus log of c. Okay, so I'll do this one, then give you another one, then that should figure it out. Okay, so let's see. We want to write this as a single logarithm. By the way, this can be done only if the base is the same. For example, if I do here this, and that's it. We cannot write as a single log because here the base is 10 for the first and the last, and the middle one is base 3. So you could combine the first and the last, but you cannot combine it with the one in the middle. Okay? But if everybody has the same base, then you can write as a single logarithm. All right, let's do it. Okay, so the first thing that you should do is any number that's multiplying the logs, you should bring it inside as an exponent. In other words, you just want to have a sum and difference of logs, no numbers multiplying. So this 2, it has to go back in. This 1/3, it has to go back in. Okay? So that's what we do first. So we're using here property 7 backwards. Is that clear? The first step? Okay, so now we have a sum and difference of just logs. Okay? So now we just do it little by little. For example, if you were, how can we collide this into a single log? What do we need to do? Did you say plus? Did you say plus? Times. Good. Remember, log sends product to sum. But you can also think of it as sending sum back to a single log in which you multiply, right? It turns sum back into products. So it would be log of x squared times 1 minus 3 to the 1/3. Is that clear? Yes?
Do we leave it as like 1/3 or do we make it a cube?
You can make it as a cube root or leave it as a 1/3, however you want. And now, remember, we need to write as a single log. There are still 2 logs in here. Now what can we do? We write as a quotient, right? So now we can write this as log of x squared times 1 minus 3 to the 1/3 over z. Okay, questions? Do you understand this? Okay. See, try this one. How about log base 3 of y minus 2 log base 3 of x minus 5 log base 3 of x minus 2. See, try this. Okay, so what should be the first step? What's the first step here? What is it? So the coefficients we made them into exponents. Good. So leave this guy alone. Then the 2. I mean, I'm just gonna leave the minus in there. Just gonna bring the 2. Okay. So if you want, technically you can always write everything as a sum, because you can even bring the exponent with the negative and everything. But then you need to understand that then you need to turn those negatives into fractions and all that business. Okay. So to avoid that, I'm just gonna bring the number itself and leave the sign outside. Okay. So I'm gonna bring the 2 inside, and I'm gonna bring the 5 inside. Sounds fun. Good. And then what do we do?
Did you factor out the negative?
Okay, very good. So we can factor out the negative. So that would be log base 3 of x squared plus log base 3 of x minus 2 to the 5. Now,
You could write it in parentheses as a single log.
so we write as a single log. What is it?
Log base 3 of x squared times x minus 2 to the fifth.
And x minus 2 to the 5th. Good. And then,
Make out a log.
and finally, we can do log base 3 of y over x squared times x minus 2 to the 5th. Good. Any questions? All right, so let me say a couple of things here. Again, this could have been done. So, we could have decided to do, okay, I'm just going to send, the 2 with everything. So let me do it with the negative. So instead of bringing 2 only, I'm going to bring the negative 2. But if I bring 2 is with the negative, a plus remains here. Do you understand this? Because this is plus negative 2 times this, right? So we typically don't write it. So what I'm saying is, when you write 2 minus 3, this really doesn't exist, okay? This is just a shorthand notation for 2 plus negative 3. So subtraction is really not an operation. We just have addition. So for computers, what they know how to do is addition, okay? It's just that we define subtraction as addition with a negative. We do have a notion of a negative, okay? And then we define subtraction as addition with a negative. So if you get rid of this, then there's still a plus in there. Do you understand this? There's still a plus. Does everyone understand these two things are the same? Okay. So that means if I bring in the negative 2, so the 2 together with the negative, then a plus will remain in here. Okay? So I can do that, and then I can also bring the negative 5 completely. And the reason why I'm doing that is so you don't have to worry about, the factoring and then doing 2 different rules. One is the product and the quotient. So by doing this, now everything is just sums. And when you just have sums, what is this all the time? These are just products, right? So now you can write this as log base 3 of y times x to the negative 2 times x minus 2 to the negative 5. Yes? Now, but as you know, when you have we don't like to have negative exponents. You have negative exponents, you need to get rid of them. How do you get rid of negative exponents? You have to use another property. What is it? You bring it to the denominator, making it positive, right? Like 2 to the negative 1 is 1/2, really. So now we do that, and whatever has a negative exponent, then it's going to come down. And all of this is happening there. But at least this way, we only use one, two rules rather than 3 rules, and we skip the factoring part. Do you understand what I'm saying? But again, it's up to you. In fact, we now can learn another model from here. Thinking about it this way, what does this mean? When you manage to have a sum and difference of a bunch of logs, right? So you bring all the coefficients inside. Let's say if you follow this way, you bring all the coefficients inside, you're going to have sums and differences. So logs that are positive, logs that are negative. Yes?
All the positive ones go in the numerator, and all the negative ones go in the denominator.
Very good, very good. Because then that means that if instead of doing this approach, you do this one, because everything will be positive, that just means that you're going to have positive exponents and negative exponents, right? The negative exponents are coming from those that were negative to begin with, and the positive exponents are those that were positive. And at the end of the day, the guys that are positive stays on top, and the guys that have negative exponents, they will be down at the bottom. So when you see an expression like this, you can easily answer it, because whatever is positive will be in the top, whatever is negative is going to be in the bottom. Okay? So instead of doing all of these steps at once, we can do the following. Imagine that I give you, I don't know, log base 2 of x minus log base 2 of y plus 1/2 log base 2 of x plus 1 minus log base 2, I don't know, of y plus 7. If you have something like this, okay, instead of having to go through all of this, the only little step that we'll need to do is bring this 1/2 inside, right? And bring it inside. I don't really want to write the whole thing, but okay, let me just do it. So we bring the 1/2 inside as a square root. And now, whatever is positive, so we know that this is going to be the log, a single log, because the base is the same, and there will be a fraction. Why there will be a fraction? Because we have positive and negative stuff, okay? On top, we're going to put whatever is positive. In the bottom, we're going to put whatever is negative. So what will be the terms on top? Who can tell me?
X and square root of x plus 1.
X times square root of x plus 1. And what goes in the bottom?
Y and y plus 7.
Y times y plus 7. So again, you can decide to do it, one at a time, like we did above. Or if you understand what I explained here on the right, then, you can think of this as a little chart, if you will, or whatever. Okay? So, it's up to you. The point is that you can get to this a little bit faster than doing one at a time. And the justification is, well, because you can actually bring the negative with you. And then you just have positive. So it's a product, but then the negative, they go down. So that's it. Are we okay with this? In condensing single logarithm, there is really nothing more to this, because you have numbers, you bring it inside, and then you just have some more difference of logs, and then you know exactly what to do. Okay, so let me give you one last property, and that one really just for evaluation purposes. Like I said, if I ask you now to compute log base 2 of 5, you may have a little calculator that has the function to do that, but mine doesn't. Okay, I cannot compute log base 2 of 5 in here unless I do something else. So how do we do that? What we do is we change base. So change of base. I'm just going to tell you a property because I really want to get to equations now. But basically, this is what it says. So if you have log base b of x, okay, you can actually write this with whatever base you want. You can write this as log base y of x over log base y of b. So the price that you pay is that if you want to change the base, here we change the base from b, we change it to y. Okay? If you want to do that, then you need to write a quotient, and then you basically divide, the log of the argument divided by the log of the base with your new base. So here you can use whatever number you like. Typically, we use this property with special bases. Like for example, if we use y equals e, then this property will read as ln of x over ln of b. Okay? But if we use it with, for example, y equals 10, this will read as log of x over log of b. Why these two special cases? Well, because these are the ones that are typically showing up in the calculator. Okay? So, for example, let's say that we want to compute log base 5 of 8. We want to know what this number is. I don't know, accurate to 2 decimal places or something. I don't have a way to do that here directly, but I can use my change of bases. I can say this is the same thing as ln 8 divided by ln of 5. And that's something that I can compute. So I can do ln of a divided by ln of 5. So this is about 1.29. Okay? Now, for example, try yourself, instead of doing ln, do log base 10, and you will get the same thing. Okay? It doesn't really matter what base you use. It's just that you have to be consistent. Whatever base you use in the top, you need to use it in the bottom as well. Okay? So, we'll give a couple more decimal places. 1.29202967. This is as far as my calculator goes. Okay? So, from now on, we start solving equations, etc. It's good practice to leave the answer in terms of ln. Okay? Or if it asks you to approximate, then you go ahead and approximate. But typically, if you want the exact answer, we leave it in terms of ln or log base 10. Okay? All right. Questions? Do you understand how to use the change of bases? It's pretty simple. Okay? You just do ln of the argument divided by ln of the base.